Hello, this is Dr. A, and in this module we are covering projectiles. And what I plan to do is split the lecture into two separate videos, of maybe 10-15 minutes each, so you don't get bored of me talking and you could replay the video whenever you want. The first video, we're just going to cover some of the basic factors that influence a projectile motion and explain how an athlete or the human body is used in terms of the kinetic chain. In fact, look at some of the ways that mechanical energy flows through the kinetic chain in order to launch a projectile in the air. In the second video, we will cover some of the basic mathematical methods that's used to resolve the horizontal and velocity components of the projectile using the laws of what's known as the uniformly accelerated motion. So what is a projectile? I think many of you know a projectile is simply an object that is in flight. For example, basketball. I'm sure many of you have been to some of the video games that are out there. You look at the guy here on the left and watch how easy he's able to get the basketball into the net there. I'll let you focus on that for a sec. If you ever been to Dave & Buster's, you probably played this game. It's one of my favorite ones. So he's doing it. He's killing it. He's scoring what is he at 425? The guy next to him is at 15. The guy to the right is 167, roughly. And it's funny is that he gets bored. Which one he's done here? He needs to call bank on that one. So anyway, as if you take in physics, you know that a projectile is any object that's in the air. So while it's in the air, it's only influenced by the force of gravity and what's known as air or fluid resistance. Now, for all the examples of projectiles that we're discussing in this class, we're going to ignore air resistance, right? This is something that we save for an advanced physics class or aerodynamics. So any sport that you can think of involves a projection. Think about it. Football, baseball, a soccer ball, anything that you need to strike with what's known as an implement. So understanding how a projectile moves, more specifically quantifying that, will give us a better appreciation of human motion from the perspective of an athlete that is throwing or that is launching a projectile in the air. So we're going to discuss some of the linear, rotary general motion of a projectile in this module. So how does the human body, how does an individual throw a baseball, or throw a football, or kick a soccer ball? Those of you who take in biomechanics lab with me know that the only way that you can maximize the velocity and distance of an object, of a ball, is by using the entire body, correct? And so the entire body, the energy through which the kinetic chain through which the energy flows in the body is governed by all the individual motions of each segment. And there are two types of kinetic chain, if you will, right? There's a closed kinetic chain in which the distal segment is fixed to the ground. Like if you're doing you're doing a squat and you're looking at how all the joint motion moves with respect to the floor and ground interaction. Or there's the open kinetic chain, where the distal segment the motion of the distal segment is free to move, and therefore its movement and ultimately the ball or whatever implement is being held by the person, its motion is a factor of all the individual rotations and motions of the segments of the body. So obviously a perfect example of this is pitching, baseball pitching here, and I've shown this video a number of times over the semester. So this is a classic pitch from the stride. Person is going through the stride phase. Front foot contacts the mound, pelvis rotates, trunk rotates, and ultimately the throwing arm rotates over into ball release so that the person can throw an 85, 87 mile per hour fastball. That is an open kinetic chain. And that ball, once it's released as a projectile, its distance, its location over the strike zone, is determined by what the pitcher does prior to ball release. There's nothing the pitcher can do to change the trajectory of that baseball once that ball leaves the hand. Now, there's going to be spin, what we call ball spin and spin efficiency and things like that. And again, that's more on the aerodynamic side of the implement. We're not going to cover that. Once it's in the air, we just know that it is under the control of 9.81 meters per second square gravity. And because we know that gravity is in the vertical direction, the trajectory that a projectile make is going to be parabolic in shape. You guys have seen this before. This is a parabola, right? And this parabola is parabolic in shape because of gravity. In the horizontal direction, its motion is going to be constant. So if it leaves the hand at a horizontal velocity of, say, I don't know, 5 meters per second, 2 seconds later, if it's still in the air, it's going to be moving at a horizontal velocity of 5 meters per second. So the only thing that's influencing its path while it's in the air is gravity. Hence, it makes a parabolic shape. Because we know that, we know these concepts, and we know that an implement or a projectile is moving in the horizontal and vertical direction, we can use vector resolution. You guys did this in, gosh, was it module 2, module 3? We used trig in order to figure out the vertical component, which is perpendicular to the ground, and the horizontal component, which is parallel to the ground. And so here's an example. You got here a tennis ball that's hitting the racket. Right here, if it's moving in this direction, this is the resultant vector of the tennis ball. And so if we knew what the angle was, the angle of impact, we can figure out the horizontal velocity as well as the vertical velocity. Same with a baseball. We can figure out the horizontal velocity as well as the vertical velocity if we knew the resultant velocity and its angle. So while that projectile is in the air, you could see here that as the projectile goes up and it eventually comes back down, the only thing that changes, as I mentioned earlier, is the vertical velocity because of gravity, and it's going to change at a rate of 9.81 meters per second squared. So as I mentioned earlier, once it's in the air, there's nothing that person can do or the athlete can do to change the trajectory of the projectile. However, it's very important if the person wants to, or the individual wants to throw at a certain distance or a certain location, there are three factors that's ultimately going to affect the projectile's trajectory. Number one is projection angle. The angle of takeoff is what I like to call it sometimes. Its takeoff velocity or projection velocity, and its relative projection height. In the second video, I'll show you how we use the laws of uniformly accelerated motion in order to figure out certain components of that projectile's motion. So going back to, say, baseball, because we know that during baseball pitching, the angle of release is at or close to zero. If you do the math, we know that the resultant velocity is going to be pretty close to the horizontal velocity. Actually, let me rephrase that. The horizontal velocity of a baseball is going to be close to its resultant velocity because it's mainly horizontal. In fact, if you look at a radar gun essentially measures the ball speed, which is the magnitude of the velocity. And so the largest component of the ball's speed is, in this case, the horizontal component. So let's take a look at these three factors. Projection angle. It's simply the angle at which the object is projected. It could be at 0 degrees, it could be 90 degrees if the person wants to throw an object directly high, in the vertical direction. You want to get jump height, for example. So taking a look at two extreme, as I mentioned earlier, if an object is thrown directly horizontally, or I'm sorry, perfectly horizontally, in which the projection angle is 0 degrees, the force will create a trajectory that is half a parabola. It's basically a semi-parabola, if you will. Look at the opposite extreme. If that same projectile is thrown directly or straight up, perfectly vertical, a projection angle of 90 degrees, it will not travel at all in the horizontal direction, so therefore it creates a vertical path that is now governed by 9.81 meters per second squared, correct? So here's a nice illustration of what I was just talking about. If you take two extreme, say a projectile that is released at a projection angle of 0 degrees, notice that the horizontal component is exactly equal to the resultant. Makes sense. And the other extreme, where it's perfectly vertical, 90-degree projection angle, its vertical component is the resultant velocity. It is equal to its magnitude. And in between here, we call these correction factors. Depending on the angle of release, will ultimately determine the magnitude of both the horizontal and vertical components of the projectile. This is trig. You guys already know this stuff. We know that, for example, that an object that is thrown or released at an angle that's less than 45 degrees would have a higher horizontal component. And an object that is released above 45 degrees would have a higher vertical component than is horizontal. We already know that. So that is just basic trig. We talked about this before, sines and cosines. So if we look at a free throw, depending on where the angle of projection is of the free throw will ultimately determine where it lands. And so those of you, I'm not very good at basketball, but I trust that you guys are. Most of you guys are, at least watch basketball. You know that a good free throw shooter is able to not only get a good spin on the ball, obviously that's important, but also have good velocity, takeoff velocity, and takeoff angle, so that the basketball, when it's released from the free throw line from the player, is able to go into the hoop at a good angle. So here's two examples here. This is where the projection angle in this case was perhaps too low. I don't know what that is, 20, 25 degrees. So the coach says, okay, you need to heighten that up a little bit. And here you got a nice little arch. You saw basketball talk about arches all the time. So in this case, they're talking about a higher projection angle. So therefore, that the ball is able to fall into the hoop. So that was angle. Projection velocity also has an effect on the projectile's path. This is the initial velocity, or the velocity at release, that ultimately is going to determine where it is going to land and how long it's going to be in the air, what we call flight time, correct? So if an object that is released, for example, at 45 degrees, this is a soccer kick, for example. If it's released at 45 degrees, technically it would, at release, would have the same horizontal velocity and vertical velocity. But because it's in the air, it is governed by 9.81 meters per second square, and therefore the soccer ball, in this case, its vertical velocity is going to change, whereas here, as it's going up, its vertical velocity ultimately is going to decrease, right? It's going against gravity, until at what point here on the top, the velocity obviously will be 0. And then it starts to increase. It then has negative velocity, and then ultimately come to the ground. The third and final factor that influences a projectile's trajectory is projection height. It's essentially the height in which the ball or implement is released. If all other factors such as projection angle, velocity are held constant, the higher the height is, or the greater the relative projection height is, the longer the flight time is. So if we take, for example, the soccer ball. This is a soccer kick right here. Show you here on the top. This is the same example I showed you earlier. The soccer player kicks the ball and it lands at the same height on the ground. So its flight time is governed strictly by 9.81 meters per second squared and its velocity and angle. If, however, we're looking at let's say a shot put, and a shot put is released 2 meters above the ground, when it reaches 2 meters on the way back down, there's nothing there for it to catch, so it's going to continue. It's just going to continue on its parabolic path here. I'll show you right here. So therefore, its flight time has been maximized, or increased in this case. On the other way, on the other extreme, this is an example where the person is going from the ground into a target that in this case is 3 meters above the ground. So its trajectory is cut off, if you will. So it obviously has a lower flight time in that case. In the next video, we'll show you mathematically how we use angle, velocity, as well as height in order to determine displacement and flight time.